All right, let's go ahead and get started today. So, actually, before we jump into this next topic, I wanted to spend a few minutes and talk about really kind of the rest of the semester and where we are at. This is still just the same schedule page where we started the quiz from, and I hope you can see that you're getting there, right? We're well on our way, right? We're sort of 2/3 of the way through the semester, and there's a little bit less of the rigid structure as we kind of finish things up here. But as part of that less rigid structure, we're going to be transitioning in the labs from doing these individual kind of siloed off labs to having this somewhat more open-ended project that you're going to be working on. So I wanted to take some time and discuss that first. There is a document that you can find there in Canvas. It's kind of listed as being under the lab, but it's really just for this week to discuss. I'll bring it up directly here in the PDF file. It's more open-ended. It presents, I think, quite a bit of opportunity for you to do something fun that you're going to enjoy. It also potentially provides some extra challenge for the end of the semester. So I don't want to read this. I know you can go through and read this entire document, but I just want to talk about my philosophy for what this is all about. I think, all semester long, I've been trying to provide these, weekly labs. Some of them have been 2 weeks long each, and they have a pretty specific learning outcome associated with them. So, last week we were looking at functions, so we were building up functionality using functions. This week we were learning about structures, so the lab had to do with using structures for that purpose. There's really only one more major topic in that sense, and that's Lab 8 associated with Learning Module 8, Lecture 8, that's on pointers. That is going to be the final conventional lab assignment this semester. It's also has some challenge to it, like I think you've seen that Lab 7 has. It's also going to be a 2-week lab associated with Lab 8. But after that, that is the end of it. And I still want you to work on something creative, kind of stretch your skill set a little bit, but I just want to give you then the freedom to kind of self-organize again now and sort of defend, propose your own project for what you may be interested in working on. I think we start with the baseline that while we have developed our programming skill set at different rates and with a different starting point this semester, you should assume, at least my assumption is, you can handle working with libraries, having function calls, having structured data, having pointers eventually, and arrays in your code. Most projects, I think, that will be interesting is a relative term, but interesting to you, and I think interesting to the rest of the class, would be something that takes advantage of more than just the standard C library. It's not just printing out, here is a list of students in the class and things like that, like we're doing in our in-class examples. And that's true of most programming, that it's making use of external third-party libraries to do some more interesting functionality here. I think to be successful, though, most projects should consider starting off as sort of an extension of an existing lab assignment, or using a library that we have already used this semester for either image processing. We'll see the example for doing more formatted fancy printing starting in lab number 8. You're not required to do that. I think that's maybe the safest approach to take. Start with a project that I know that works, modify that versus starting entirely from scratch and maybe struggling really to get started. But that depends on your background, your comfort level as well, and what other experience you may or may not have. Teams are going to be of size 3 or 4. Teams are up to you. The TA is there to help if the teaming arrangement doesn't really work out, or you can't find a good team, or you can't find yourself on a good team. If you love your lab partner, stick with them. That's fine. You're not required to split up from them and form a new team, but then combine with another group of 2 and form a team of 4. When I say of size 3 or 4, that's also a function of the number of students in a given lab section. So we have to kind of make the math work out at the end of the day. Because the idea is your team will be based on those who are all in the same lab section. You will still be going to lab each week. It'll be a little bit of a different kind of feel to it because everyone across the different groups will be working on something different. So the TA will be providing more general guidance, but the thought there is that's at least a guaranteed couple of hours while you work on this that everyone on the team should be expected to be available. There's a couple deliverables here. The first deliverable will be this project proposal assignment, and this is an assignment. It is an assignment worth 0 points, so in some sense you can't do a bad job or you can't negatively impact your grade. It's really being just checked off for completeness, but it really will be to your team's benefit to put extra thought up front about what your project is going to be about, versus trying to just submit something last minute because there's no points you're going to lose with regards to this particular assignment. A little bit of planning now can save you a lot of grief kind of later on. That's the first part of the assignment. There's then going to be sort of a final presentation slash demo, which will be during what would otherwise be scheduled as our final exam time. Don't recall which day during finals week that is, but we'll figure it out when we get a little bit closer to that time. So we will come here. We will actually have a 2-hour time slot during that day, during final exam week, and those will be presentations from each of the teams, presumably a quick demo of what your code does at the end of that as well. I mentioned each team will be given an 8-minute time slot. That depends on the number of projects we have, and I'll just make sure the math works out for us in terms of how many minutes you have for that. I may also ask teams to give a kind of mid-project update. That'll be a pretty informal thing we'll do in class on a subsequent Wednesday likewise. The challenging part when you have a more open-ended project, and you'll see this in a lot of courses, this isn't unique to this course, but any course that has a project aspect to it where I'm not telling you what the project must be, is it can sometimes be a little challenging to have really sort of a fixed grading rubric associated with it. What does it mean to get an A on your project? My approach, which is shared amongst others, but not all my colleagues in the department, is to really allow you as part of your project team to define what success is. You get to define within reason what a successful outcome is going to be for your project, and I'll just hold you to that. So that's both challenge and also an opportunity that you're not being limited by what I say you must accomplish. You get to propose your project, defend what would be a reasonable score across different categories or characteristics of your project, and then just kind of defend it. And actually at the very end of your project, when you give your presentation, I'll even ask your opinion at that point as well. Okay, here is the grading rubric you came up with. There's some structure to it should follow. Here's how we think we did. And I won't necessarily take that number, but I'll take that into account when doing my own evaluation of that particular project there. The assumption generally is this is kind of sort of like maybe 4 weeks of lab work, or at least the complexity or scope of it should be roughly 4 weeks of lab work. So the total score will be 200 points. So this definitely does provide an opportunity. If you've been part of a lab team where some labs have gone well, other labs not as well as you would have liked in terms of the score you're able to get, with this rubric, with this effectively 4-week lab that this project winds up being in practice, you can really increase your lab score and really help your overall grade in the class if that's something you are concerned about. When I originally had this assignment, I didn't have any project ideas and it stressed out people. So I have since added a number of project ideas that you can consider, but you are certainly not limited to any of these project ideas. I won't go through all of them. They're really just kind of starter suggestion. They're not fully fleshed out ideas. But for example, we did have a lab assignment that was a barcode generator assignment. Some of you really hated that assignment. Others did just fine with that assignment. If you enjoyed it, using the libgd library to generate a very particular pattern based on some input sequence, kind of the 4-week version of just doing that would be something like a QR code generator. Doable. Maybe understanding a little bit of the math or the algorithm behind it requires a little bit of work. So I say conceptually, maybe it has a high difficulty because you have to be able to read either spec sheets or Wikipedia articles of exactly how QR codes work in practice. But then once you get a handle on that, I do think if you're able to do the barcode example, you could do a QR code generator. All sorts of games are kind of fair play. For example, Connect 4 is a very common kind of final project for an introductory programming class. 4 in a row game. To me, that's an interesting project if there is some sort of AI opponent. Technically, Connect 4 is a solved game, meaning that if you go first, you can guarantee you will win every time. That is a little tricky to implement as an AI, but it's doable. There have been teams that have done that. That's why I say the programming complexity of that varies depending on how deep you go into that aspect of things. I don't want to see 5 different Connect 4 implementations. So one thing I'm going to ask teams to do, kind of informally, as you form up in lab, starting next week would be an appropriate time to do that. As you decide, okay, the 3 of us are going to be a team, the 4 of us are going to be a team, I want you to post in our Discord in the projects channel, just kind of staking your flag in the ground and saying, we're going to do Connect 4. And unless there's some novel difference between 2 different Connect 4 implementations, I really, for the most part, just want one team to do Connect 4 and one team to do Advanced Minesweeper. If 2 teams really desperately want to do Connect 4, that it's been your life's goal to implement Connect 4, that I'm not going to stand in your way. But I'd like to see something different between the various teams. We will have, as part of Lab-08, a Minesweeper application. And you may think, well, how could I possibly implement Minesweeper? Like anything else we've done, we have to plan it out, we have to kind of draw it out, we have to think about it, and we have to kind of scaffold our way to a solution from kind of a bare bones version. You will be able to do that in lab number 8. Still kind of a basic version. If you wanted to make a more advanced version, you can. That's true of Minesweeper or any kind of like console-based video game. If you want to do a proper interactive video game, there's all sorts of libraries that would help you with that. The main challenge with a proper kind of graphical interactive game is Replit itself might be the limiting factor. We may have to go outside of Replit to actually implement that to get reasonable refresh rates and things like that of the code. Replit itself is slow enough to kind of make that not as fun as it otherwise could be. You can build a Discord bot. Students have done that in the past. That connects to our Discord server, and every time a student asks a question, gives an answer or something like that. If you like chess, you can work on a C interface to the Stockfish chess engine. These are just some examples here. You are not limited to these examples, but if you're interested in any of these examples, you can plant your flag in the ground. You can come talk to me in office hours. We can discuss some of the parameters of these projects. They're all potentially fun. They're all potentially quite challenging, but I think if scoped appropriately, at least in my mind, looking through these examples, they're all doable. You can succeed in any one of these projects. You may think, Pac-Man is beyond me. Pac-Man's a real video game, and it's tens of thousands of lines of code. Well, it can be, but it's also doable. And I don't know how well it's going to run on this system because it was trying to update the code here. This is from last year. This is just a team from last year. In fact, they were using the chat feature, which we haven't been using that much in Replit. And some of their last comments were kind of the night before saying, I can't get it to work, it's crashing, and things like that. So it was kind of fun that at the very last minute they were still working on it. We'll be setting up these as shared Replits, so you won't have to be emailing code back and forth or screenshotting. You'll all be contributing to the same project. Maybe we should have done that all semester. We'll be doing it for our projects at least. I was having a little trouble building this because some of the library names have changed in the meantime. But last I checked, here's Pac-Man. It is no audio. But given the limits of Unicode and finding a Unicode-looking Pac-Man symbol was a little tricky, they got something that I would say reasonably well worked, right? Yeah, it's doable. And you may think, how do I implement the ghosts? Well, the ghosts are just algorithms. The ghosts for Pac-Man are very well documented exactly. And I didn't realize this until I saw their project, that there's it's broken. There's 4 different ghosts, and they have 4 different AIs, but they're not AIs in like the modern sense. They follow 4 different well-established algorithms, and you would just implement those as you go. This is something that you have the background to do. You just have to think about it a little bit in terms of, okay, I have a board, how do I implement that? I have ghosts, how do I implement that? How do I visualize the result on a screen? This is using that Curses is the name of the library that you will get a chance starting in Lab 8 to play around with. And what effectively allows you to do, it's not that different from just printf. In fact, if I can see a little bit of the code here, there's some setup code that's not super fun. Instead of doing a printf, just to give an example, you instead specify close to a printf type call, it's just called something different, where you provide a grid coordinate first. You're saying printf at this location in the screen. And then once you have that functionality, you're doing a lot of the same things you'd otherwise be doing, but it's a little bit more manageable to handle something like, here's Pac-Man's position. I'm going to draw Pac-Man. I'm going to do a print W, MV print W at this particular location. There's a little bit of extra setup. There's a little bit of extra kind of gotchas to do that versus just doing printf. We'll sort all through that. We'll have enough examples that you can start and build your own console-based game if you so choose to. Let me talk about the rubric finally in terms of what I actually want you to submit. I want to make sure you have your teams set. I say at least 24 hours before the due date of this assignment, but earlier is probably better. Again, if you have 2 teams, they like each other, combine to a team of 4. If you want to kind of become a free agent and join a group of 3, become a group of 3, that's fine as well. Kind of trusting that you're sufficiently responsible and adult enough to form your own teams, and I don't have to babysit that process all too much. If you need my help or the TA's help, let us know. Want you to post your high-level ideas in projects. Your Canvas, the submission is going to be a 1-page PDF write-up. And again, you can last minute this, but you're really only potentially harming yourself. I want just a brief overview of what you're hoping to accomplish. I want you to really think about a list of project goals, like how do I get from this concept I want to implement, what steps is that going to require? That requires planning. You can't just quickly riff on it. You have to really think about the problem for a little bit first. So you have 2+ weeks to work on this. Take some time and think about the project versus just, oh, this would be fun. I don't know what it would take, but it would be fun. Start with that, but then drill down into it. What would it actually require? If possible, depending on your project, a quick mock-up of what the potential end project demo would look like. It's good to think in those terms anyway. You can just hand sketch that if you want, or you can mock that up however you'd like. What would the end result look like? A very high-level project timeline is sufficient. Just know that these things always take longer than we would expect, and integrating code together oftentimes takes much longer than we would expect. Team member A is going to work on this part, team member B is going to work on this part, C is going to work on this part, and then we're going to integrate it all together. That's a very common approach. Give yourself a couple weeks for that integration part, because that can be very challenging. Some of our abstractions kind of break through when we haven't truly thought about what those interfaces would be. Finally, and most importantly, and where the majority of I want you to spend your time on for this part, is to provide your own grading rubric for that. That is how you will be evaluated. I will take your word for it. When you submit it, you may get a feedback from me in Canvas saying, well, tweak this and resubmit. But for the most part, you submit this rubric, this will be your grading rubric. Put it together carefully. This is an example rubric. One doesn't have to follow this, but here's how a rubric typically looks. We've seen them in Canvas for just our own lab scores, but they're pretty high level. Oftentimes we have a series of attributes. Those are our rows in the table of our rubric. Those are generally meant to be technical milestones or characteristics or features of your project. That's the rows of our table. We then also recognize that it's oftentimes not a binary thing, whether or not we have a particular feature or characteristic. It's not, yes, we have it, or no, we have it. It's oftentimes a sliding scale of, we have made reasonable partial progress for it, or we have actually met all of our goals, or we actually did more than what we originally expected, or we kind of stretched and really enjoyed this part and did even more for this particular attribute here. Those are going to correspond to your columns of your rubric. This is not meant to be that it has to be called beginning, unsatisfactory, low level, but that's the thought. First column is kind of partial points, partial progress. Middle column is meant to be got an A, did exactly what I wanted to do. And then give yourself the ability that if for one particular or another feature or characteristic, you perform even better than what you would hope, or it's a stretch goal you can think of it as, give yourself additional bonus points for those as well. You'll provide that rubric. The grading will be based on my evaluation of how you performed across those categories. The goal is that if you hit everything under accomplished, satisfactory, medium level, the different phrasing I use there, that is supposed to add up to 200 points. So while you have a little bit of flexibility here, I generally want you to have 5 total attributes with 3 different performance levels for which that middle column adds up to 200 points. You can then have that rightmost column add up to 300 points. So as I mentioned, those of you who are kind of perhaps worried about your lab score in this class, the assignment is out of 200 points. If you get 300 points out of 200, and it has happened before, that's like kind of 2 free labs you've given yourself points for. That should do very good things for your overall grade in the class. You want to have your attributes be something that can be evaluated kind of fairly and succinctly as well. They're not meant to be total judgment calls. It should be kind of clear between your team and myself that, yeah, for this attribute, you use printf scanf. For this other one, you included initialization via .csv file. And so it should be a pretty straightforward thing. It's not always 20 or 40. I'm allowed to give you 30 or 35 or 25 points for a given attribute. But it should be pretty clear generally where your performance lies. So you want to avoid kind of squishy language or just arbitrary judgment calls. In fact, one of the attributes I listed here was project organization. It's fine that you can do project organization, but some of these are kind of judgment calls. So even in my own documentation, code is well documented. Well, what is well documented? That's a judgment call, what it means to be well documented versus poorly documented. Final presentation and demo is clear and understandable. clear and understandable to whom. It's also kind of a judgment call there. You're on safer footing, and you'll, I think, go into the project with more confidence if you put together a rubric that is really kind of cut and dried and kind of factual in nature. And that will allow you to say, as you're making progress on it, well, I'm really stuck on attribute 2, we're struggling here, but look how great we did on attribute 3. We're actually doing just fine on the project. You should generally know what your score may be in a given project here. Finally, I want to mention, and this does happen every year, that your goal when proposing this project and when putting together the rubric is not to impress me, like on a personal level. Your goal is not to show like just how incredibly difficult of a project you can come up with. Give yourself a project based on discussions amongst your team and the interest area that you picked for the project. Scope your rubric so that you can get a 200 out of 200. I am perfectly happy. I said this on day one, and I believe it hasn't changed. I am perfectly happy with every single student in this class getting an A, because it means you've gone through the appropriate steps, and I'm happy with every project getting a 200 out of 200 on their rubric. So keep in mind the time you have to actually spend on the project, roughly 4 weeks with a team of 3 or 4. And just like for some of the harder labs, I do expect it's outside of the lab time you're working on this, but it's not a full-time job either. I'm not expecting you to be putting 30 hours a week a person, to accomplish this project. It is not a senior design project. It is not a master's thesis project. It is, a final project for a 4-week period of time for an introductory programming course. It's okay if you have big goals. Set your rubric accordingly so that given a reasonable time investment, you can get that 200 out of 200 on that project. That's what I mean by don't try to impress me. Oh, look, we proposed the world's hardest project, but I'm still going to hold you to that, and then you won't be happy with your resulting score here. Give yourself various ways to succeed. Give yourself a scope that you actually believe you can accomplish, assuming a good faith effort across the entire team over the remainder of the semester that we have here. That's my pitch on the project. Questions, thoughts, concerns? Okay. Step 1, find a team. Step 2, attempt to agree on a project at least a high level. Step 3, kind of plant your flag, saying here's what we're going to be working on. Step 4, take the remainder of the 2+ weeks you have to work on this, carefully put together your rubric. If you have any questions about your rubric, if you're not sure you've done a good job, you can always reach out to me and ask me. I will review, evaluate, check off each rubric. For many of them, I may provide specific feedback that you need to fix this attribute or tweak this attribute. But for the most part, I will take your rubric. That'll be what I score your final project on. No questions, thoughts, concerns? Okay. Pac-Man is doable. I believe their rubric was the game is fun to play was one of their rubrics. And that was actually tough because is this fun? I don't know. It's cool. Is it fun though? That's debatable.
Imagine yourself back in 1986. Pac-Man's still pretty fresh.
1986.
You just got a cool quarter and you put it and you play it at the arcade.
This is fun, you're right. 1986. Where would I have been playing in 1986? Probably not Pac-Man, not even in 1986. We would have been well on to like, what would have been the hot arcade game in 1986? I'll let you look that up. I was certainly there. You were not collectively as a group here, but I was certainly there in 1986, wasting plenty of quarters in the arcade. Okay, so if there's, oh geez, that seems dated too. Okay, could be. Maybe it was Pac-Man then, 1986. The NES came out by then, so we didn't need to waste nearly as many quarters in the arcade then. Okay, let's kind of transition on to what our kind of final key fundamental topic is in C programming, and that is that of pointers. My job, I think, with this topic is to demystify pointers for you. I don't think you will become experts in pointers either by finishing this topic, by working on the labs for it. It is just something that is just very sticky and tricky with working with C programs. I want to make sure you understand the concept. When it comes time to actually implement it, I recognize, and I want you to recognize, you're still going to be making lots of bugs, creating lots of bugs with regards to pointers in your program. Because it's not just you, it's people who've been programming for years and years and years still make lots of bugs create lots of bugs in their programs as it relates to pointers. We've been playing around a little bit with it, but now we're going to treat it a little bit more formally. I want to make sure, and I think probably most importantly, the conceptual analogy. What does it mean to have a pointer? We've done a little bit of that. Let's do it properly now. An important thing for us to then also understand is kind of the pointer array equivalency. We've been playing around a little bit with that this semester, and I just want to make sure we're really solid in understanding that concept. And then as a directly related, but something we haven't played around with at all yet, is that of dynamic memory allocation. It is directly related to pointers. How do we allocate objects that are not of a fixed size? How do we resize objects? How do we delete objects in our code? This is not an especially enjoyable part of C, but if you want to put C programming on your resume and you want to go out for an internship that does C programming, you have to be able to do this. This is kind of what separates those who know C from those who've maybe tinkered with C. We'll get there. It still just takes practice and takes experience with working with it. This will also be the code for this reason, that as you write your code on Lab 8, possibly then for your projects as well, you will find your code crashes quite a bit more now than what has done in the past. Because once you start playing with pointers, if you do not initialize them properly, if you do not deal with dynamic memory allocation properly, kind of the default result is your program crashes, not that you get like a compiler or other kind of incorrect result. Looking back at functions, this is just part of the motivation. We saw that there were some limitations with this basic structure. This is just one motivator for pointers. That we have a function name, we have input arguments, and we have a return type. We have one particular return type associated with that function. Somewhere then in that function's implementation, we would have a return statement that given a variable of that type, we will eventually return some either constant value or some variable of that return type for that function. This is an example that does a saturation operation. Given an input as well as a minimum and a maximum value, saturates it to either the input or output, saturates it to either the input minimum or input maximum and returns that value. It's a saturating filter, right? So given an arbitrary input range, your output range is kind of clamped to the initial part, the minimum or the maximum there. That is a very classic use of our functions here. And we know that functions can just be called by themselves, or if it has a return type, can be used anywhere you expect a variable of that particular type, including being on the right-hand side of an assignment statement. So that saturate function here, and the details of this function aren't what are really critical here. One can call it by itself. That is syntactically valid. It will not give you a compiler error. I don't even think it'll give you a warning, but this is a function that returns a float. If you don't then use that variable, that return type anywhere, the function is not really doing anything meaningful. There's no point in having called that function if you're not actually returning that type here. More commonly is you would then take the function call you have and use the assignment operator to return a variable and to override a local variable of that type. But those functions can go anywhere you expect a variable of that particular type. Whether this is good coding practice or whether this approach where you have a temporary intermediate variable is kind of a judgment call, but anywhere, if this function has a return type of float, anywhere you expect a variable type float, you can instead have a function that returns of type float, including in the middle of a printf there. We already saw as kind of a pain point or limiting factor of functions is that while there's all sorts of scenarios we can come up with in which you have multiple input values and exactly one output value, there's probably equally as many scenarios in which we would want to potentially change more than one variable per function call. We played around with a couple of the workarounds for that. We can have an array. If you change an array of values, that changes multiple things. We can have global variables. That's how we did that for the playing card example from earlier. Kind of a hack because there's kind of the side effect of all of your functions. Static variables allow you to change potentially multiple things for function calls. This approach with pointers is one motivating reason we have them. It allows us to change multiple things per function call. And I mention that because we've been doing that all semester, from kind of the first week, right? When we wanted to read in an input value via the console, via the user prompt here, we have this great function, scan formatted, that allows you to provide kind of an arbitrary amount of type format specifiers, and you would then overwrite an equal number of variables that are specified at the end of the function here. And using that syntax we've kind of taken for granted, When we forget it, the code just doesn't work, and then I tell you to add it and the code works again. That ampersand operator or that address operator. So here is our introduction to pointers. Here's our very high-level view of memory again. I'll try not to repeat myself too many times, but this bullet point here is all that matters with regards to pointers. Pointers are nothing more than a variable type for storing an address in memory, which we then can use to directly and indirectly refer to other variables. That is all that a pointer is. It is a variable, a special type of variable to store an address in memory. Put more succinctly, pointer is an address. An address is a pointer. That is all that it is. We have our conceptual view of memory where we declare these variables, and we know that each of these variables correspond to a certain number of bytes that are eventually ultimately stored in memory once the program is executing. Separate from that, we have these separate type of variables for which we don't store the value of something corresponding to an integer or a float or a structure. We store the actual address itself. That is what a pointer is. It is a variable that stores an address in memory. We've already done pointer print or a version of pointer print before. But in my code here, for example, I'm just declaring an int A and an int B. A we happen to initialize, B we didn't happen to initialize here. And when it comes time to now print the value of the address in memory, we create a pointer. That's what that address operator, that ampersand operator is doing. We're saying, don't print out the value of A or the value of B. Give me the address of A and the address of B. And there's just a special separate format string specifier to print pointers. You could print it as an integer as well. That would also work, or as a hex value. That would also have worked. We oftentimes don't need to print the raw value of pointers. So it's more of an indirect way of accessing things versus us actually typically caring what the actual address is. But if we want to know what the actual addresses are, we can find that for our programs. Really long hex looking string here. We've perhaps a 64-byte address space here, so we get a 64-bit address space here, so we get a 64-bit pointer back out for that particular application here. We can then separately, syntactically, declare a pointer as its own type of variable. We'll talk more about the syntax, but I just want to show it in this example as we print out the addresses. Here, I'm declaring not that C is an integer, and it's just hard to look at that line of code and not think of it that way, but you have to kind of get used to that starting today. Int star C is saying C is a pointer to an integer. And for better or for worse, we have to say what type of thing we are pointing to. That's why we say int star versus just star C or some other pointer keyword that doesn't exist in the language. Line 9 says we've declared a variable. It is a special variable of this pointer type that's meant for storing an address in memory. In this case, it is intended to store the address of some integer. We can then set that pointer, conceptually at least, like we store and overwrite or use any other variable we have in our program. C is meant to store an address in memory. We have to have some mechanism for storing an address. One such way is to take some other variable that's already going to be put on the stack of this function and just to get the current address of it. C is going to be overwritten as the address of A. When we do that, the value we wind up printing out for C for its address, and if I wanted to be more precise, I think it's probably better to say not address of star C, but like address of C is that value. The address of the actual pointer, and it's the same value because we've initialized it the same value. So it is a variable that allows us to store an address in memory. Okay, beyond this workaround for functions having multiple inputs and things like that, the whole point of having this address, this pointer variable here, is that we can then indirectly update things in memory via that address. So we'll talk more about the syntax of how this works in practice, but I have this pointer variable called C. Star C, again, is called following the pointer or dereferencing the pointer. Neither is a great word, but maybe follows closer to what we're doing. Get the address, and get whatever's in memory at that address, and that's what I actually care about. That's what star does. Follow the pointer. Whatever this arbitrary high-level address is, go there in memory. And at that point, once you've followed the pointer, what you get back out is that integer. You get back out whatever was in memory at that location, interpreted as whatever the pointer was pointing to, in this case, pointing to an integer. So for this line of code, what do? I say star C, follow C, that address, and set it to be 3. Consequently then, when I print out A after the fact here, it almost seems like kind of a side effect that happened, but it's very intentional, at least in this circumstance. I haven't touched the value of A directly in my code. I initialized it to 2 on that first line. But because I've updated the memory that A is located at, when I go to print out A after the fact, A has actually got a value of 3. It's no longer a value of 2. Probably you can see why this is going to make your programs more complicated, right? It's hard enough just to kind of track the value of A in and of itself in your program. You have your loops and your if statements and your function calls and all the things that potentially mess with A. And now you're seeing that potentially all sorts of arbitrary code in your program can update A as long as it has A's pointer. And so tracking that becomes a more challenging thing to do. The value of why we have that is to give us things like scanf, where we can update multiple things in our function call, because we're not actually changing it. It's still an input, but the input is an address. And because it's an address, we can indirectly update the value of A and indirectly update the value of B, because given the address, we can do exactly this. We're just going to have an awkward pause while you walk out. Oh, it's awkward for me anyway. Okay. Address of A, address of B. There are some location in memory. Again, oftentimes we don't actually care what that address is. I mean, there's some circumstances when you have a particular device and you're trying to access some control information on the device, you may need to know exactly what address that thing is located at. But oftentimes for general purpose programming in this kind of environment, we don't usually care about that arbitrary address here. I can show that if instead of setting C to be the address of A, I instead do some dynamic memory allocation, the address will look quite different. That is memory that's being located on the heap versus on the stack. If instead I have some global variable D, it's going to be somewhere else entirely, I believe, than those 3 locations. So that's at least from an educational perspective tells you something. Variables that are placed relative to the function, the so-called stack, are given some really high-looking addresses on this particular system. Variables in memory that is dynamically allocated, and we haven't covered this yet, go somewhere else in memory. That's referred to as the heap. And variables that are global, kind of the global memory address space, go somewhere else entirely. But beyond that, kind of just to know where my variables are, we usually don't actually care about the actual value of the address. Oh, this should be at 404.014. Oh, I actually want it at 404.018. We're usually not managing memory in that sense. But being aware that we have these variables that are storing these addresses allows us to conceptually do things like updating things independently. You'll notice, because I changed the pointer, when I have star C equals 3, the value of A is still 2 for those examples. I didn't update A anymore because C, by the time we get to line 17, is no longer pointing to A, it's pointing to D. We've updated something. In fact, if instead I were to print D instead, then that should be set to 3 now for the same exact reason. Here's my mediocre pointer analogy. Our previous analogies have not worked all that well. I have a key. That's our analogy to a pointer. It usually specifies the location in the mailbox or in memory where I can access mail or access data. So the 333 is labeled on the key. That is the value of the pointer. We usually don't care what that value is, but we know there is a value. It corresponds to one particular mailbox, one particular location in memory. I then use that key, that's the referencing or following my pointer, to to open the mailbox 333, to read the data at address 333. And then I have the mail. I have whatever content is in the mailbox at location 333. That is corresponding to the data at address 333. Once I have that open mailbox, I can do whatever I need to do with it. I can read it. I can modify it, equivalent to reading or writing our data variables that we have here. Where this starts to get a little bit icky, and this also happens in our real programs as well, is okay, the pointer is a key, but the pointer is also a type of variable. It's a special type of variable for storing addresses. So this key itself would also be stored in some location in the mailbox. So technically you can have a pointer to a pointer, or a key to a mailbox that holds a key to another mailbox. And for all sorts of reasons that will eventually become apparent, we actually tend to do that all of the time. We typically don't go more than pointer to pointer to pointer, although you will find some examples where that is the case. But still, while the syntax for that starts to get a little ugly, and wrapping your head around it when you're looking at someone else's code, I think understandably can be a little time consuming. If you always think of that pointer as being a key or a variable that stores an address, then having a pointer to a pointer is just a variable that stores an address of another variable that happens to store an address. Same for a pointer to a pointer to a pointer. It's a key to a mailbox to a key to a mailbox to a key to a mailbox. Conceptually, that is all our pointer is meant to be. But I agree that this is a mediocre pointer analogy. Here's a much better pointer analogy. Yar, here being me pirate treasure map. There's the pirate, and ahoy, me pirate booty. So this analogy is maybe a little bit better. It's certainly cooler because the memory as mailbox analogy only goes as far as that we don't really unlock memory. Right? There isn't a locking and unlocking, at least not via this pointer mechanism. The pointer being closer to like a map with like an X marks the spot maybe also is a little bit more reasonable. Here's where you need to go to find this variable in memory would be another way to think of what a pointer actually is here. Let's leave things here for today, but I encourage you to come back on Friday. We're going to play with pointers. We're going to learn pointers. We will not be experts in pointers. That will only come through time and experience, but we'll get closer, okay?